going to do, I'm actually going to hand something out to you. Oh, no, not going to happen. Excuse me. Last year you did some transformations of functions, right? Whether you remember or not, I know you did. So I'm going to give you just the top third of this worksheet, the notes sheet, I guess we can call it. The top third of this piece of paper, I want you and your pod to spend a couple minutes coming up with the equations. For this activity, you have y equals x squared as your function. And I want you to write 6 different equations based on the description I have listed. So write me an equation of x squared that has been shifted right 7. You have about 2 to 3 minutes to, as a group, come up with some answers.
Because when you apply to this, and then the up and down is down. Yeah.
Okay, let's chat all together with what we have. I like those of you that were experimenting with your calculators to see if you had it right or not. That was a good idea. Okay, so we'll start off with the 4 easier ones, right? Pod 1, shifted right 7. Okay, pod 2, B.
Y equals parentheses x squared plus 3.
Like this?
Yeah.
Okay, so there is a difference between A and B. Right? Which one is the notation that we need? Sully.
The square root on the out, or the square root on the outside of the parentheses is right.
You think?
I know.
Okay, I like that better. The square actually needs to go on the outside because if we want something to affect our graph horizontally, it needs to be inside the function itself. Okay? Let's talk about shifted up 4. What would that look like? 3.
Y equals x squared plus 4.
Okay, so this is kind of what you guys had. You just put parentheses around it. Okay, the parentheses really didn't do anything to the function itself. Does that make sense?
Yeah.
Okay. Pod 4? Well, yeah, you're pod 4. Letter D?
We have y equals x squared minus 6.
All right, good. If something is on the outside of our function, it affects it vertically. So these are shifted up or down. Okay, how about vertically stretched? I'll take a volunteer.
Is it 2x squared?
2x squared would be a vertical stretch. Did anybody have something different?
Right. Parentheses x squared.
Okay. Yeah, that would be fine, like this.
Yeah.
Yep, that would be fine. That basically reiterates that 2 is on the outside of the function. Okay? It could be 2. It could be a different number. And we'll talk about the specifications for that different number. Okay? But good. Reflection over the x-axis. Someone besides Sully.
We have y equals negative x squared.
Negative x squared. Very good. All right. Now, thumbs up if, yeah, that was pretty easy for me to remember. Thumbs middle, I remembered most of it, but some of it was a little rusty. Thumbs down of, oh my, I don't remember that at all, and it was a struggle. Okay, so wherever you were on this little thumb scale, okay, we're going to go through the transformations. We're going to go through 2 examples and my expectations for what I want to see on your graphs. Okay? Let's see if this is going to work. Yep. Okay, so we'll just erase these here. Isn't that cool? Okay, translate the graph left C units. We're going to do all of this in function notation, so you could apply it to anything. Okay, if we wanted to move to the left, what did we need to do? Add where?
Inside.
Add inside the function, inside the parentheses. And to shift to the right, we subtract inside the parentheses. If it's inside the function, it is affecting our graph horizontally. And because not everything can be simple, right? When we have something inside of our function, it does affect it backwards from what we want to think, right? X minus c is a shift to the right. Okay, it's a little backwards. I know some of you may have struggled when you first learned that. Okay, shifting up or down C units, we want C to be where? Outside. Add it outside if we want to go up. Subtract it outside if we want to go down. Reflections involve negative signs. Where is the negative sign if we want to reflect about the x-axis? Okay, out in front. About the x-axis is going to affect the y values, so that's vertical on the outside. Which means if we want to reflect about the y-axis, we want to move those x-coordinates, so we need something inside of our function. Okay, 7 and 8 are the fun ones, right? Okay, the stretches and shrinks. This is where it really takes a little bit of patience to keep things organized. So vertical. We had a vertical stretch on that intro part, right? Okay, so we had a value multiplied to the outside of the function. Okay? Outside, it's affecting it vertically. Okay. Now, everybody picked a number. Well, everyone picked 2. But really, if you want to stretch, that number has to be bigger than what? 1. If C is bigger than 1, then it is a vertical stretch. If C is less than 1, we have a vertical shrink. Okay? Now, in order to apply this transformation, okay, you're going to take all of your y values from your parent function and you're going to multiply them by c. Okay, you're going to take your parent function y values and multiply them by c. And that's all it takes to stretch it. Or shrink it, I guess. Okay, so our last one, a horizontal stretch or shrink. What's that going to look like? Okay, that C has to be with the X. Okay, because it has to affect the horizontal. Okay, someone said it's going to be opposite. Who said that? Okay, what's going to be opposite?
is greater than 1.
Okay, these rules get switched around. C is 1 is greater than 1 is a shrink. C is less than 1 will be a stretch. Okay, if you think about it, if we are stretching something vertically, then it looks like it's being shrunk horizontally, right, for the most part. If we think of like a parabola or an absolute value, if we're stretching it vertically, it's getting shrunk horizontally. So those rules have to be backwards. Okay, now, just like up here, okay, to shift a graph C units to the right, it looks like minus C, but we're actually adding C to our values, okay? So to apply this one, I'm going to write it over here because I have some weird message right there. So to apply, we're going to multiply our x's by 1 over C. We have to be backwards. You multiply your x's by 1 over C. Okay. So like I said, I'm going to do 2 examples. I do not care if you do these examples on the back of that note sheet or if you do it in your notebook. But that note sheet will be helpful as far as like a reference when you are studying for all of those rules. Okay. So here's our first example. Please write it down. Parent function, what is it? X squared. Okay. Please do not write down the graph that I'm about to draw up here. But when you think of the parent function x squared, these are the 3 points I want you to think about. We know that the vertex is at 0, 0, and then we know we have points 1, 1, and negative 1, 1. If you focus on those 3 points, you can do the stretches, reflections, and shifts without an XY table and very quickly. Visualize these 3 points. You can draw them if you need to and then transform. But these are the 3 coordinates I need you to think about as you shift them around. Okay? All right. Describing the transformation. Okay? Kylie, what is this 1 doing right here? Okay, so we have a shift, right, 1, okay, and this minus 2 right here. Victoria, what does that mean? Okay, we're going to go down 2. So those coordinates that I pointed out, okay, really let's just think about the vertex, right? Our vertex is normally at 0, 0. We're going to shift it right 1, down 2. I need to see that coordinate. Well, you can't just draw U and call it good. I need to see that it has the basic shape of the parabola that hasn't been stretched or shrunk. So I need to make sure that you put these other 2 points right here before you draw your parabola. That way I know you did not stretch it or shrink it. What do you think about that? Yeah? Okay. With any graph, I shall ask for domain. Aaron, what do you think about our domain?
All reals.
All reals. Any polynomial will be all reals. Okay. And our range, Sierra. Where do we have y values? Above where? Above -2? Okay, good. So we're going to write that as -2 with a bracket because we have -2, and then to infinity because it's above -2. Okay. I would say a third of your test on Tuesday will include writing things in integral notation. A third may be like kind of pushing it, but there's a lot that you have to write in integral notation on Tuesday. Okay. All right, this last part, I have students who like panic about what it means. All I want you to do is I want you to take this transformed function and I want you to write it in function notation. So f of x is our x squared. So basically, wherever there's the squared, we're changing it to f of x. All right? So g of x, instead of x minus 1, the quantity squared, we're going to write f of x minus 1. Because x minus 1 is inside the square. It goes inside of our function notation. And then minus 2 is after it. So we're going to put it after the function notation. And that's all I need you to do. Basically, change out the parent function for the function notation. F of whatever. Okay, now I know I yapped a lot, but how long did it take us to graph that? Okay, if I would not have talked, I think we could have graphed that in about a minute, maybe even less. Okay, no calculator, no table of values. Just think about the parent function, move it around, boom, we have a graph. We can think about domain and range quickly. Okay, it'll help us when we get to more complicated stuff. All right, let's do one that has more than just a couple of shapes. Okay, parent function, what is it?
Square root
Okay, I am going to talk about the parent function square root of x, so you kind of know my expectations for the transformation. It begins at 0, 0, and it goes through 1, 1. Bare minimum, you need to think about those 2 points. Okay, those are 2 easy points to think about, right? What would be the next easy point to think about? Okay. You can think about those 3, or you can just think about 0, 0, and 1, 1. Okay? We don't need a calculator. We don't need an XY chart. We just know that those are points on the square root function. Okay? I'm going to leave that there. The transformation. What is this 2 doing, Zane? Okay. And then that plus 3 is doing what, Isabel? Okay. Let's talk about the order in which we do transformations. Always, I want you to do a stretch or shrink first. So we have to multiply things together, and it's just going to work better if we do that with the most basic parent graph. Then if there's a reflection, do the reflection. And then, very last, perform your shifts. Okay, what's first? Stretch or shrink, then reflection, then shift. Okay? So this is what we're going to do. We're going to take these coordinates, we have to vertically stretch them by 2. Remember, we are vertically stretching, we are taking the y coordinates and we're multiplying them by that c value. So what is the y coordinate at this point? 0 multiplied by 2. Okay, then we shift it left 3. This coordinate right here has a y value of 1. When we multiply that by 2, it becomes a coordinate 1, 2. Then we can shift that coordinate left 3. That would be enough for your graph, but just let's practice one more time. This is the coordinate 4, 2. If we stretch the y coordinate by 2, it becomes 4, 4, because we multiply that y value by 2, and then we can shift it left 3. And so there is our square root function. That's a big stretch. Okay, can you tell it was kind of taller? Right? Okay. Domain. Emma.
So it'd be negative 3.
Why don't you look at the blue graph one more time? Here, I'll get rid of the green one.
It's negative 3.
Good. And we include negative 3. Good. It starts at negative 3 and gets bigger. Okay? Range. Bracket 0 to infinity. Okay? Good. And then when we write in terms of f of x, remember, whatever is inside the actual function, that's what's going to go inside the function notation. So x plus 3 needs to go inside the function notation, and 2 goes on the outside. Okay, it's the time you've been waiting for. Oh, hold on, not yet. I want to remind you about one thing. You've been waiting for this greatest integer function, right? How many of you looked up the greatest integer function on your own? Okay, it wasn't that you were not that anxious about it. All right, before I get to the greatest integer function, though. Okay, I'm hyping it up because I think it's awesome. Okay, please do not fall to the trap that this is a shift right 4. Remember, I told you shifts have to happen last, and reflections need to be applied first. If there is any sort of coefficient with that x, it has to be factored out because it does affect the shift. That negative has to be factored out so that we can see this is really a shift left 4. Okay. Same thing were to happen if this was like 2x minus 4. You would have to factor the 2 out. Any sort of coefficient has to be factored out so you can apply them separately. Okay. Now the time or not waiting for. The greatest integer function, I'm going to give you a definition that I want you to write down. And then when it's time to graph it, if you want to grab your pink sheets to graph it, that would be fine. Okay? But the greatest integer function has this notation. It's like double absolute value bars. Pretty cool. And it means the greatest integer less than or equal to what is inside. The greatest integer less than or equal to x. So if 2.3 is inside the greatest integer function, what is the greatest integer less than or equal to 2.3? 2. Remember, integers are numbers like -2, -1, 0, 1, 2, 3, 4, etc. What about the greatest integer less than or equal to 1.9? It's actually 1, which feels awkward because we're used to the rounding rules, right? We're always going to round down, even if this is 2.999999999. Okay, the greatest integer that is less than 1.9 is 1. Make you think again. What about -1.5? Okay, if we're rounding down, the direction down, we would go to -2. When we get to the negatives, we kind of have to think about that number line. Okay. What about 3? 3. Okay, if it's an integer, it gets to stay as an integer. Okay. Did I make you panic with that one? Okay. All right, so what does the graph look like? What do you think it looks like?
Stairs.
Looks like stairs, okay? This is called the step function sometimes because it looks like a set of steps, okay? What's happening? Okay, you have a coordinate at 0, 0 here. Anything between 0 and 1 gets rounded down to 0. But then once we reach 1, it gets 1. Anything between 0 and 2 gets rounded down to 1. But then once we hit 2, we get a jump up to 2, and etc. So we have all of these little horizontal bars that look like steps. Okay. You have a book assignment. Okay, cross your fingers.